Howdy, so we're at example 5, still in the topic of functions, and we're looking at the 2018 paper example or question number 8. So the first question is to derive f prime of a function f of x, which we're given from first principles. Now, importantly, this equation, which you will be using, is given in your formula sheet. So you don't have to memorize it by heart. But I thought it would be good to just explain this a bit. So we've got some kind of curvature, it doesn't really matter. And so the slope of a line, which is, well, the slope of a tangent line between 2 points on this coordinate or on this graph or figure would be, let's say we have a point here to the left, that's x. We have some kind of distance here, which is h. And so the point here is x plus h. Okay, and remember this h is nothing but a distance indication, a symbol used for distance, so that can be L also, but in your case it's h. Okay, and then what we've got here on the y-axis is the function value, okay, at the point x, and here on the y-axis is the function value at the point x plus h. Okay, now if you can recall the slope of the tangent line, that's nothing more than delta y over delta x, okay, and this is where this equation stems from. So in this case, this delta y is, well, you can see it over here. It's this top value, f and the point x plus h, minus this f and the point x. Okay, and this delta x, well, that's nothing more than this length of the section. And that's indicated at the bottom. Okay, so it's nothing more than the slope of the tangent line, or a slope of a line. Okay, so, and it is as the point, or this, as this length gets reduced in size and approaches 0. Okay, so let's do this example then and implement this equation. So in terms of notation, we can write df dx, which is also notated as f prime of x. Okay, these two things are equivalent. And that equals, according to first principles, the limit in the point h approaching the length of 0. Okay, and now we're applying this equation over here to the specific function that they were given. Okay, so the top part, we have x plus h squared minus 5. Okay, that's related to this part over here. Okay, next we have to minus, and now we're going to apply this part of the equation. Okay, so that's just minus x squared minus 5. Okay, and we're going to divide it still by h. Okay, now we have to simplify things in the top here a bit. Do that. It's still written as the limit of this length of h approaches 0, and we get x squared plus 2hx minus 5 plus, oh, I should do that a little bit better. Let's not skip ahead of ourselves. Plus 2hx, so I'm multiplying this bracket by itself, plus h squared minus 5 minus x squared. And I'm taking that minus into the bracket here, so it becomes plus 5. Okay? And everything divided by h. Okay, so let's see what cancels out a bit. This minus 5 and this plus 5 cancels out. This x squared minus x squared cancels out. And what we have crucially here is a h in both of these terms. So what we get is, well, that equals the limit of h approaching 0. And then we're going to take this h out the bracket. There's a common factor. We get 2x plus 1. Plus h, sorry, my bad. And divided by h. Okay. Can these two cancel out? And we're left with the limit of h approaching 0 of 2x plus h. Okay, and as h approaches the value of 0, the answer therefore is that f prime of x equals 2x. Okay, easy peasy lemon squeezy. Next example. We're asked to compute dy dx of two different functions. And now we don't have to use first principles anymore. We can just do it as is. I hope that you can remember how to compute a derivative. I'm not going to explain it in detail here. I'm merely going to do the examples. You can follow along. And as soon as you see something that you don't understand, I suggest you go back to a video that explains the concept of determining a derivative in detail from like first basic foundational principles. Okay, this is not the aim of these videos, so I'm going to look for it. Okay, so we have this function y, that's fine, and we have to compute it with regards to this independent variable x. Okay, so the solution to this problem is as follows: plus 12x plus 1. See if you agree with that answer. And if you don't understand what I did, go and check it out on another video. And this over here is written strangely. It's meant to confuse you, but you shouldn't be confused at all. So what you see on the right hand term over here, there's no y's, but on the left hand term there's 2 y's. Okay, so you've got to just rearrange the equation a little bit to get it into standard form like this: y equals da 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 da. Okay, by inspecting this left hand side of the equation, you can see that both these terms contain a y. So perhaps it's a good idea to, for a first step, to take out this y as a common factor. Okay, let's do that, and we get x minus 1. Okay, and by inspecting the right hand side over here, you see, oh, well, x is also a common factor between these two terms. So perhaps it'll be nice to take that out as a common factor. I get x over here, and I get 2x minus 1. Does that look okay? I don't know. Did I make a mistake? Yes, I did. Because what I could also see from the right hand side over here is that there 2 is also a common factor. So I'm going to take out 2x. Okay. And then by taking out 2x, I get left with x minus 1. Cool. I can get rid of this x minus 1 by dividing it on both sides. Okay, and now very simple. This whole very complicated, intimidating equation here gets reduced to y equals 2x. And now you've got to compute the derivative with regards to x. and that's nothing else than 2. So at the end of the day, it's a very easy derivative to compute, but you just have to do some factorization. Okay? Easy, and that's 4 marks. That's a giveaway. I'm going to do one extra example from first principles that I thought was good, and then we'll be done with this topic, I think, because it's nice and easy. Okay, we're asked to compute the derivative dy dx for this function. Cool. We're going to apply the equation. I'm going to write dy dx equals, well, the limit of some distance approaching 0 of fx plus this distance minus f in the point x, or the function in the point x, divided by this distance h. Okay, this is the limit of this distance approaching 0. Now we're going to apply this the point x plus 1, x plus h, my bad. Okay, so we're going to get 2 x plus h squared plus 3 x plus h. Okay, that was the first part. Second part is minus. I'm just going to rewrite the equation for this. So it's 2x squared plus 3. Okay, and all of this shizzles gets divided by h. Now we're going to do some simplification. Never drop this limit equals h approaching 0. Simplification gives us 2. I'm first going to multiply this bracket over here by itself. So it is x squared plus 2hx plus h squared plus 3x plus 3h minus 2x squared minus 3. Everything divided by, you guessed it, is 3x. Oh, I made a mistake here. It's 3x, 3x. Okay, everything divided by h. Cool. What gets cancelled out? We've got a 2x here and a 2x squared. If I multiply this 2 into each of these terms, okay, which is what I have to do, cancels out this 2x squared, and there's a minus 2x squared. There's a 3x here and a minus 3x there. So I'm going to just write it out slightly simplified. It's skipping over stuff too much, otherwise it gets confusing. So we get 4hx, it's this term over here, plus 2h squared plus 3h. I don't think I made a mistake. I'm hoping. You can double check me. Okay, everything divided by h. What do you see here? What jumps out of the page? Well, all of these terms over here have an h in them. So we can take that out as a common factor. These cancel out, and we get that dy and dx equals the limit of h approaching 0 of 4x, plus 2h plus 3, and so that equals, that thing equals, it approaches 0, so that equals 4x plus 3. Double check yourself. Does that make sense if you just derive it? Yes, that's cool. And that is the derivative based on first principles.